Look at that, it's a miracle. So I'll pre-apologize, Richard Steenbergen again, or Turkbergen, depending on the results of the survey, from Global Turkbergen Telecom apparently. I'll pre-apologize for the, I don't know what the waving means. Closer, okay. I will pre-apologize for the lack of pretty pictures in this because I literally just finished this during the Q&A of the last thing. So, what the heck is this all about? For anyone that doesn't know, a jumbo frame in Ethernet, technically anything that is bigger than a 1500 byte frame, according to the IEEE 802.3 Ethernet standard, is a jumbo frame. It's outside of the standard and therefore not standardized. So the question is, how much bigger? What makes a jumbo frame? What do people want to pass as a jumbo frame? And the answer is no one really knows because, of course, it's a non-standard. So the rough guideline that we're all kind of working on right now is around 9,000 bytes. And that's really a historical number from the original Alteon proposal from about 15 years ago for an even 9,000. But for most vendors today, it's actually a completely different number, but it's somewhere in that ballpark. Insert meme picture here. So the goal of jumbo frames, there's three main goals. The first one is to improve high-speed transfer efficiency. So if you look at the way most hosts, most CPUs work, and most operating system works, they're really not built around moving 1500 byte packets, or even less once you factor in all the overhead of headers. They're really built around moving data in at least 4096 block chunks, the size of a memory page, the size of a block writing to disk. Pretty much anything is that type of block. So when you start breaking this down into 1500 byte packets, it actually doesn't align with that very well. So in classic days, what you had was you had to wait for the operating system to do all this chunking and buffering and waiting for buffers to fill and do all this extra work when copying stuff. So you did more copies into memory, you did more segmentation, it added load. The second goal of jumbo frames is to reduce the packet per second count. So if you go from your standard 1500 byte to say 9,000, that's a 6x increase in size. So if you're sending all content, you might be looking at 1/6 the numbers of packets per second. And again, 15 years ago, packets per second was a big deal. It was a big concern that was a major cause of the load and impact on devices, was how do we keep up with all these lookups. And the third argument for it is increasing the flexibility when tunneling. So 1500 bytes, because of Ethernet, are really the de facto standard of the internet. You really rarely see packets that are larger than 1500 bytes go across the internet. And so that's why tunneling 1500 plus tunnel overhead is so hard to do. So the intended use of jumbo frames is a little bit different than historical. So the way that it works today is pretty much everyone tries to go up to the maximum. You take your 1460 of TCP data or whatever it is minus all your options, and you shove it into every packet, and you're going to have your packets be almost always that size, and any packet that isn't is probably an ACK for a packet that was. The way that we're proposing, or the way that jumbo frames propose to be used is differently. Instead of sending a 9K packet every time, you're really sending 4096 or 8192 of payload plus whatever you have in headers. And so in theory, it makes it easier to support tunnels, to support different media types, to support maybe an IPsec tunnel, things like that. That's the goal, is to not to get to 9,000, but to get to 8192 plus something, and then have enough room for that something. And we're now starting to see some inter-network deployment. So until very recently, jumbo frames were pretty much an internal network only thing. You know, if they were ever going to be used anywhere, it was when you controlled your own network, and it was very easy for you to know what you set on both sides of a link. But now we're actually starting to see some IX operators start to roll this out to some major exchange points. There's a lot of cases where they're using a dedicated VLAN and telling people what the MTU number is, and they're trying to do all the right things. And this could, in theory, eventually lead to being able to do a greater than 1500 byte packet end-to-end, and that's the goal. So there's a lot of people out there who are cheerleading this effort, and there's a lot of idealism about improving the efficiency of high-speed flows, and maybe someday we'll get these beautiful 100 gigabit flows to people's houses. But I'm here to talk about how that's all a bad idea. So, sorry. So first off, big problem with jumbo frames is really picking the number, because remember, there's no standard value defined anywhere, nor is there any way to actually negotiate this for you. So really we're down to manual negotiation between operators. I've got to call up the person on the other side of the link and say, what value does your gear support? What number do you want to configure, etc. But it's not even that simple. It's made harder by the router vendors because even the numbers don't mean the same things. So for example, when you're on a Cisco iOS device and you talk about a 1500 byte MTU, on a Juniper or on an iOS XR device, that actually means 1514 because one side is including the Ethernet header and the other is not. But it's even worse than that because on the side where you're including the Ethernet header, it changes depending on your encapsulation. So if you have a VLAN tag in there, you've now got to go configure it for 1518. If your interface is configured for Q&Q, you've now got to go configure that for 1522. And so every time you do this negotiation with the other side, you've got to understand what gear do they have, what number are you actually talking about. And the really bad part about all this is if you get it wrong, you silently black hole traffic. That's where it goes really bad really quickly. So path MTU discovery, which is the mechanism for detecting mismatch today, in a word, sucks. The way that it works is when a router encounters an MTU mismatch, it has two interfaces. It received a big packet over a big interface and it's trying to send it to a small one and it can't fit. It will drop the packet. It will send back an ICMP message, as was talked about in the last presentation. And then the host is responsible for receiving that ICMP message, detecting that there was a problem, and reducing the packet size on this flow from now on. But that doesn't work very well. So first off, if you look at the architecture of routers and how they generate ICMP, that's not a hardware performed function. That's what's called a slow path. You have to drop the packet, punt it to a CPU to generate an ICMP message, which can only happen at a certain limited rate. So there might be a cap of 100 or 1,000 packets per second. So it's incredibly easy to launch a denial of service against this. All you would have to do is generate some big packets that come through a big interface going to a small interface, and you've taken out this router's capability of ICMP generation. You probably broke traceroute in the process, but you definitely broke path MTU discovery. The other big problem is that ICMP is all too often blocked or limited by the ISPs, the users, pretty much any random person on the internet who gets a little filter happy will block the ICMP message. And while there's a dedicated type for it, most people aren't that discriminating, and so that's where you start to see problems. So the only reason that the internet works today is really because of the de facto 1500 byte standard. If we actually encountered path MTU mismatch on any type of regular basis, we'd all be living in a lot bigger world of hurt than we are today. Other problems that people forget is the larger packet size increase the jitter. So, you know, a 100 gigabit flow, some beautiful high-speed end-to-end flow is a very noble cause, but you've increased the amount of serialization delay by 6x. So now you've got someone on a slow-speed DSL or cable link at home, even a nice 10 meg link, you've added 6.2 milliseconds of serialization delay. So something that people don't take into mind when they're building for the very large flows is that it's probably not going to achieve anything. It might actually hurt the home user. The benefits here are completely non-existent until you have 100% jumbo enabled end-to-end path. It doesn't help you in any way if one piece in the middle is bigger. And there's really no content network who's ever going to risk rolling this out. The benefits are minimal, and the risk is that they're going to break some flows for some customers. And not only that, but they're likely to do it in really obscure ways, where some flows go through, the connection starts to open, and then the connection ramps up and it doesn't go through at all. And worst of all, this is all completely unnecessary. So remember, jumbo frames are about a 15-year-old idea, and 15 years ago, that actually helped. You by cutting the load factor by 6x, by cutting your memory operations, by making your buffer page flipping and whatnot more efficient, you were actually able to take your 300 megahertz processors of the day and make them deliver potentially a gigabit flow. Today, it's really completely unnecessary. So the modern NICs support what's called LSO, large segment offload. So instead of it now the host having to do all this work of managing these fragmentation and segmentation of all these buffers, it'll just hand the NIC a single, here's a big 64K write, and the NIC will then take care of doing all the segmentation and offloading. And it does it very efficiently. in a way that it's not causing a problem. So really we're talking about solving a problem that we really don't even have. So the other argument is that having jumbo frames will help you with tunneling. So if you now have a link that supports something bigger than 1500, that makes it a lot easier to implement a tunnel. And it's an interesting argument, but really I think it proves the point that path MTU discovery is so fundamentally broken. Because if MTU mismatches actually worked, you wouldn't have a problem tunneling under 1500 bytes. The fact that you're having that problem proves exactly what you're hitting. So all you're really doing is creating more MTU mismatches to try and solve the problem of MTU mismatches, which is just making your problem worse. So then the question becomes, what would it take? What would you need to do to actually raise the bar on MTU? What would be required to do this internet-wide? And I think before you can even begin to try and dabble in this space, you've really got to have some type of reliable negotiation between the endpoints. It's not sensible to have operator A call operator B and say, what do you want for this link, and then try to figure out what they mean when they give a number. You need some type of negotiation protocol. So if you think about what you need, it's Ethernet, so you really need to support this per MAC. You need to be able to support this per next hop, essentially. And if you look at the way the hardware works on most modern routers, it actually does support it that way. So if you've got a /24 subnet, you can give a different MTU value to a .2 versus a .3, but that's not exposed in any software. But if you look at the underlying hardware, the capability is actually there. But then in order for path MTU discovery to ever have a chance of working, you would need to know about it at layer 3. So the only sensible place that I can think of to put something like this would be in ARP. When you're negotiating between the two hosts, you could negotiate what the MTU that the end devices think they're capable of passing, and then hope that your layer 2 device in the middle gets it right. And the problem there is that's a really dirty hack that's very unlikely to get implemented. Getting ARP changed at this point is pretty much not going to happen, so no chance of that really happening. But this all comes back really to the fundamental problem of path MTU discovery, and that's where the whole thing fails. If you think about what you're trying to do, you're requiring the router to drop the packet, generate an ICMP, have that ICMP make it all the way back to the host outside of its flow before the host even knows that there's an MTU mismatch. The host then has to react. It's completely unsupportable on the modern router architecture. It's, like I said, vulnerable to denial of service, and it really adds latency and stalls the performance on every flow. If you've got to wait for you to hit this, have the ICMP generated, have it come back, that's not a fast thing. And if you look at the work people are trying to do on the internet, taking out a couple of 100 milliseconds of round trip time from just the setup of the TCP session and the initial windowing, we're going in completely the opposite direction. We're now adding significant latency that's tied to the CPU of a router. So we want to talk about customer complaints. Every time someone does something to run at the CPU on a router, it's a really quick way to get there. And there's really no replacement on the horizon for path MTU discovery. That's the big problem here. So supporting jumbo frames doesn't really do anything to help you, and trying to use it makes the problem worse. So in short, just want to have a counterpoint to the people who are pushing this on IXs and saying this is a good thing. My take on it is it's probably going to cause a lot more harm than good under the current technology, and I don't really see any replacement technology in the future. So something to keep in mind. Questions? Yes.
Hello. I'm Darius from Akamai. Isn't a possible solution here basically better standardization, in that we standardize on a specific MTU, then say routers implement a single binary flag where either on this MTU or not, so Cisco and Juniper can, work together and fix their stupid number, whatever is going wrong there, and then the interconnection network MTUs becomes a lot easier?
That would be a much better way to solve the problem. The problem is the IEEE has steadfastly resisted any effort to do that. They refuse. It's been brought up many times, and they refuse to consider putting any other value in. And I'm not going to fight the IEEE, so.
Okay.
Leo?
Leo Bicknell, Farsight Security. Two comments. One is on the tunneling. I think perhaps the mistake you have made is you have assumed that people want to tunnel layer 3 IP packets with something that looks like a router. They in fact may want to tunnel layer 2 packets where there is no way to send a packet too big. They may want to tunnel non-IP protocols. They may even want to tunnel layer 3 without having the tunnel look like a router that could send back a packet too big message. So I think you're being a little too dismissive on the value of being able to move a greater than 1500 byte packet for tunneling purposes. The second comment I have on the ARP thing is I agree that perhaps changing the actual ARP protocol is not going to ever be possible. But I am fascinated that no one has made an attempt to negotiate a layer 2 MTU, because it seems to me like a amazingly trivial problem. You assume everyone has a 1500 byte MTU, you send an ARP, and if you get back a ARP reply, followed immediately by the, hi, I'm a new thing that knows much bigger MTUs and, well, whatever else you want to stuff in that packet, then it can send bigger packets. I mean, yes, there's some details there, but I would be shocked if that was a 10-page RFC and more than a couple of hundred lines to implement. So I don't know why people haven't gotten on fixing the layer 2 MTU negotiation problem.
Yeah, absolutely. So there's lots of ways you can attempt to skin that cat, and that's definitely the only sensible way to do it. Really, what I'm trying to point out here is that we're not ready for prime time. We're not ready to roll this out and have people try to achieve jumbo frames over the internet. And there's a bunch of concerns, and this is one of them. So if people could start paying attention to that and do some standardization work on it, you'd probably go a lot further.
I will say that as a user that has configured far too many tunnels in my day, greater than 1500 byte actually works about 99.99% of the time. Where it does not work is to consumer connections. If you want this on your cable modem or your DSL link or even your T1 to your house, probably ain't gonna never happen. But almost all backbone providers are clean, bigger than 1500 internally. And in my experience, the vast majority of PNIs are clean, greater than 1500 bytes. So when I try to tunnel a greater than 1500 byte packet, admittedly like 1600, not 9000, my success rate's like 99.99%. And the only place it ever breaks is when it goes over a public exchange.
So I'm not sure I would agree on the PNI part. I haven't really seen a lot of interest on the PNI side for people doing that. And then really the interesting question becomes how many broken things are sitting out there that we don't know about because we're not trying that greater than 9,192 and less than 9,216 range. And I think the answer is there's a lot. I've run across that more often than you would imagine. And as soon as people do start trying to send those packets, you're going to suddenly have broken flows and no one's going to know why or where to troubleshoot it. Yep.
Wayne Bashar from Limelight Networks. One of the things that's frustrated me with this whole MTU issue is the fact that when the call for additional bandwidth has come into play, say for example the transition from FE to GigE and GigE to 10, is that people did not take advantage of the opportunity to say, all right, we recognize that there are certain problems in the underlying architecture, the underlying protocol and specification design. So we're going to make this incompatible, just the way that a DS3 doesn't talk to a SONET connection, and make the router reframe it and be able to take advantage of some of the improvements that could be had, and allow over time, the same way that you rarely see an FE connection on an end device anymore. They're still out there, but they're getting fewer and far between, and allow time to take care of solving that little problem to be able to allow us to get to bigger MTUs. The way I look at it is when you're talking about higher and higher bandwidth, the 1500 byte MTU, 10 gig, 100 gig, it starts to look a lot like ATM, where you have so much of your overhead being thrown away because of or so much of your bandwidth being thrown away because of overhead with these little tiny small packets and this really big fat pipe that you start to introduce some enormous inefficiencies and some real cost, some real expenses and real cost losses into your network. But he's commenting behind me as well that creates buffer problems. If the standards bodies were to be able to do something like that in going forward in future technologies, do you believe that that would have a significant impact on reducing the problems that you've identified and perhaps being able to allow us to be able to do bigger things with fewer problems?
Well, it's an interesting problem because, every time they change the protocol, they make significant changes to the layer 1 side. So no one has a 10 gigabit hub that will talk to a 1 gigabit device. But it's hard to say we're not going to make a switch that is compatible with both 10 gig and 1 gig. That's going to throw out a lot of your business, a lot of what Ethernet as a protocol is intended to do. So I understand why they hit that problem. In terms of efficiency, I mean, do the math. 20 bytes, 40 bytes of headers per 1,500 bytes versus 9,000 isn't in the same league as ATM. It's not quite that bad. So yeah, it's a slightly inefficient, but the question is, are you actually gaining enough in efficiency to make it worth all of the problems that you're going to hit? And I'm not sure the answer is yes, based on everyone else coming up with perfectly reasonable solutions to handle all of this load.
Well, if to respond to that, you look at the increasing demand for larger and larger and larger file sizes, not just in terms of the source for an on-demand stream, but also in just bulk data transfer to end users. The ability to deliver that is directly proportional to the amount of data that you can send in a single packet. So there is a real reason to want to do more data in a single packet, just to reduce the turnaround time on a data transfer.
Also true. Yeah, that's one of. I should have thrown that in as a reason, but there are technical reasons why it's a help. The question is it worth all of the suffering, or do we need to do more work before we start trying to roll it out? And I think that's the point that I'm trying to make. Is I'm not saying that it's not technically lots of good benefits, but we've got to solve those problems, or we're going to cause more problems than we solve.
Right. Well, my purpose is just to say, all right, let's look at the people who are defining the standards, the people who are producing the products, and say, all right, we need help. So.
Hi, Eric Klink from Equinix. So on IX and on lit services, we have a lot of customers who have a little checkbox and it says, do you support jumbo frames? And you spit out 9216 or 9124 and they go away happy. And we know from stats that absolutely nobody puts jumbo frames across any of our IX platforms. I have a feeling that applies to the other IXs in the room. Are we making things worse by having 9124 as the MTU or whatever other people have, or a certain individual who pushes 9,000 who's in a car on his way to Florida to not defend himself? Are we making things worse, or is that just okay at this point?
So the reasons I think it's making it worse is, while you might have done a great job of making sure that everyone that's on your IX is using the same value, you've picked a different value than another IX. And so the real potential here, the real thought is, how do you cross these points multiple times and have path MTU discovery work? And the problem is, it's so broken as a technology that once you start hitting any type of MTU mismatch, whether it's at a single exchange point or whether it's across two, you start breaking stuff. And then the reason that I'm doing this presentation is because a lot of people are happy. They come in and they say, oh, jumbo frames, that sounds like a really good idea. I like better performance. I like, faster flows. And they don't think, what's the downside? So I want people to be aware of that and be a little more cautious before they start turning it on. And there's a lot of things out there that are going to break when they go over those flows as soon as someone does try to send a big flow across.
So would it actually be better if we all got together and picked a number and all went with it? Or still broken? What's the suggestion here?
The all would really have to be the IEEE for it to have any hope of going anywhere. Yeah.
So, Bill Manning, large frame cheerleader. Shouldn't your email address be changed?
Why?
Rat. But that's not, that was my complaint. The question I have has to do with the fact that large frames, the negotiation for large frames or different framing MTUs has been around for longer than you have been alive. And the mechanisms that we have in place, as you described, were for a simpler, kinder, gentler time. What we have now is the same problem with two different vectors pulling on it. One of them is the increased signaling rates on the links, 10, 100 terabit speeds, right? And it's increasing, and if you stick at 1500 bytes, you increasingly start to look like the ATM problem of the 53-byte cells and reassembly, which leads to a buffer bloat problem in the intermediate processing, and you have that whole back-off problem and all this stuff that you're talking about. The question is do you do the short-term, it's cost-effective to eliminate any upgrade and migration strategy to support a newer, different internet interconnection modality just to make the quarter profits? Or do we actually provide constructive quality feedback on how do we actually do this? If Mike Sinatra would get up and talk, the Internet 2 community, the R&E community have been doing jumbo frames for a long time and some serious studies on jumbo frames. It's got to start somewhere. Pushing it at IXs and backbones is a reasonable place to do it because that's where you have the high bandwidth. It will throttle eventually, but it'll throttle close to the edge. And quite frankly, you can fix the MTU issue, and you can also re-enable TCP on port 53 at the same time. Thank you very much.
So if we talk about eventually when we're at 1 petabyte Ethernet or something, yes, eventually we're in the billions of packets per second, 1500 byte MTUs is going to look bad. The question is 9,000 any better? Is the 6x benefit really worth it? Or do we need to find a way to do 60x, 6000x? Where's our 64K MTU?
All right, we have about three.
The problem is the number changes, and the number changes a lot. So what we need is a mechanism to negotiate this and actually make it work when the MTUs mismatch. That's what needs to happen before you can achieve any of those goals. Not to say that they aren't admirable goals, but we have to approach it from that perspective or we're going to break a lot of stuff in the process. So while it might be great in the core, as soon as it gets to the edge and you hit an MTU mismatch and you break the consumer, that's a problem.
We have about 3 minutes remaining. Let's get the last two questions in if we could.
Let's do.
Scott Librand, Limelight Networks. It sounds to me like you're not complaining about jumbo MTU, you're complaining about jumbo MSS, which is to say you don't want the servers to actually try and use 9000. Having it in the core for purposes of tunneling and whatever is great as a band-aid for the other problems that we have. I wonder if maybe the most pragmatic solution here is to simply have the TCP stacks do their own path MTU discovery that doesn't rely on routers sending packet too big messages. Like if I send a 1500 byte packet and then I have another packet to send a millisecond later and I make that one a large packet and then, except do it in the other order, do the large one first, then the small one. If I get an ACK on the small one, a selective ACK that says, I didn't see your big one, then I know that that's a broken path MTU and I can go back to 1500.
Or
it
that
should
you
be
had random packet loss or any number of other.
Yeah, but there should be ways for the TCP stack to heuristically determine whether it's likely to be successful at 9,000 bytes or not, and do that in a way that doesn't degrade performance because you're only doing it after you ramp up the window a bit. I don't have all the answers of how that would work, but it seems like given that the problem is the MSS and not the MTU, we should be trying to solve this in TCP stacks, not in networks.
Well, like I said, we definitely need a replacement for path MTU discovery, and yes, the best way to handle that would be to make it in-band as part of the TCP flow instead of having the network try to handle it. I'm not saying that jumbo frames are horrible. There's clearly some technical advantages, and I would like to see that capability. I'm trying to make people aware of all of the downsides and risks, make sure that they don't go then try to enable this on their hosts and try to push out packets.
I agree. Setting an MSS of 9,000 has lots of dangers.
Yep. Last question.
For what it's worth, Paul Barron thought that jumbo frames were a very bad idea. If my memory serves me correctly, jumbo frames were created by Sun Microsystems in 1993 as part of the specification for NFS version 3 and the creation of the so-called fast Ethernet standard. And the IEEE had the good sense not to include the large MTUs in the fast Ethernet standard. To me, this issue is all about what that guy yesterday was mentioning, I forget his name, about NANOG versus IETF. The people in this room know how to make things work, and in IETF they know how to tell you why they shouldn't be done. And I think that this whole jumbo frames issue really emphasizes his point, is that there should be more interplay between NANOG and IETF. Their food is better anyhow.
That's definitely a problem, and I was talking about the most recent iteration of jumbo frames trying to come back as pushed by Alteon around 2000 with Gigi. But yeah, the problem here isn't even the IETF, it's worse, it's the IEEE. So the IETF actually proposed jumbo frames, and the reason that they put forward was to support very large as-is topologies. And the IEEE said that's a horrible reason and rejected it. So even the IETF is on the side of jumbo frames and didn't really get anywhere with it. Yes, overall, we definitely need better communication between the standards bodies and better explanation of why we need what we need, where we need them. There's probably a good way to handle this, but I don't think that turning on jumbo frames across the IXs or across anywhere else and trying to shove big packets down the internet is the right way to do it. So,
Thanks, Richard.
thanks.